Assalamu alaikum. My name is Ahmed Ali Ghazi from RK53. Today, we're gonna present to you how to design a bandpass filter using ADS program, and we will show you the steps, how to design the filter and how to do the calculation uh, in the ADS using the line calc utility. So first, you open the ADS, then you create a new workspace, you name your workspace and save it, and then you can create a new schematic. You can name your schematic, up to you, and then you are ready to put your components. First, you need to choose the resolution technology that the ADS can reference to do the calculation, the other stuff, and for us, we will choose this 1 micromillimeter, and then now you can start put your components. Anyhow, for to fast up and to explain to you faster, I already prepared in advance our circuit design, and I'm gonna explain to you how to do it. Okay, guys, after the program has loaded up, now as you can see, this is our circuit design, and you need to get this component by searching in this search bar. This MySub, it help us to simulate the results, and you need to add the specification of your filter, like the height and the ER, the dielectric constant, the cone, the HU, all these stuff you can find from your substrate. And for this project, we are using the Roger Droid substrate, and we are using specifically the 5880. And as you can see, our substrate is 2.2 here, and we have to add it here in the substrate in the MySub. And this is the 5 ohm transmission, and you can search for it by writing term and put it here, and then connect the other stuff. This is the cable line, and the name is MS fill, and these will do that you will do the calculation on to calculate the width and the length and also the spacing between these cable lines. And for our project, we use a three order filter, and for the calculation, we are doing for the GSM 850, and this our frequency will start from 896 megahertz until 893 megahertz. This is the uplink band. So this is the calculation for our center frequency and then the fractional bandwidth. We need to do this calculation to get the admittance interval that will help us to do the Z odd and Z even. So after that, we can use the line calc utility to help us calculate, like I said, the width and the length for this cable line. So for this calculation, first you need to use these two formula. These two formula is for the first and the fourth components. I mean the first and fourth cable line, and then this one is for the second and the third component. So first you need to find your fractional bandwidth, and like I said, from this calculation you put it here and then multiply with pi. And for G1 and G2 you can get it from this table. We use the maximally flat table, and For us, we use the nth 3 order. So this is for G0, it will be 1, G2 will be 1, and so on and so forth. So if you do the calculation, you will get the first and the fourth will be the same, then the second and the third will be the same. And also, if we go and do the calculation for ZO, which I will put the equation later on, as you can see, these two supposed to be the same, and these two supposed to be the same, as we can see in the ADS system. So to calculate the W and S and L, we need to go to Tools and Line Calc, Start Line Calc. Okay. As you can see in this window, you have to change the milling into the MC line, like we said here, because we are using a couple line, and the couple line need to have the 2 lines here. Okay, after the loading complete, so you can see we have the couple lines here. This is the how we can do the calculation. So first, you need to put this specification as same like your substrate. So like I said, the ER you need to find it from here. The thickness of the metal, we leave it here as gold, and then the tan and D you need to find it in your substrate. And then also you need to change the frequency to megahertz, because our center frequency, like I show here in this calculation, it's in megahertz, 800 to 81 megahertz. So after doing all of this, you can start putting your Z even and Z odd from the calculation you did in the table I showed you just now. So each pair here will represent one couple line. So after doing this and press synthesize, you will get 3 values here. You just need to change to millimeter first, so you don't confuse yourself later on, and then you just copy paste the values here. After done all of this and making all the connection is correct, you need to find the S param, because we need to simulate for the S domain, and you need to put the start and stop point in between your to cover the range of your frequency. So if we do the simulation, it will show us the following. So as you can see here, this is for our simulated result that we need to do some tuning for. The red line represent the S11 and the blue line represent the S21. To get this one, it's just easy. You need to take this one, this palette, and then choose S11 dB, then S21 dB also. But then you can get, after a bit of zooming, you can get so the result that you want. And as you can see, it's pretty the same. And as you can see, these are the same things. And then you can add some markers and to show. I will show you the marker thing after I do the tuning.
Assalamu alaikum. My name is Muhammad Umar from Yemen, from RK53. And in this part, I'm going to explain in the transit analysis on our microstrip filter. So this is our schematic. As we know from my friend's explanation from the previous circuit, that we had 2 terms in the schematic. We had 2 terms, term 1 and term 2. We added to the circuit this term, as you can see. Okay, this one. The previous circuit we added 2 terms, this term 1, term 2, and for this part we are going to add VT sign, this one, and also we have add R 50 ohm and the ground to the ground. This is VT sine. This term we add here, uh, and for the calculation, actually it's almost the same as the previous calculation we did. And sorry for this filter order. It's actually order three, and filter response equally wrapper. And the other calculation almost the same. We have the impedance 50 and the frequency response 881.5 megahertz. Okay, now we will do this the center frequency. As we can see here, we add it, so we can do a simulation. Let's see. Okay, right, in our simulation transit, as we can see from the waveform here, this is the V out in millivolt response. Here we start by 0, and then after 800 and above, which is our frequency, our center frequency 881.5, it will change the response. Here the response, and this is our Vn versus V out, and this is the Vn. What will happen if we change this frequency, this center frequency? Like for example, we want lower frequency, like 700 megahertz. We try to simulate what's the result we will get, or the response. Let's see. As you can see, here's the new response of under our new frequency. So more frequency means more output we get. So that's all.
Okay, guys. My friend was explaining about the transit response and transband analysis. And now I will show you how to optimize the performance of the filter. There is one tool named tuning in the ADS. And this tuning let you choose the parameters that you want to increase or decrease the width, length, and the spacing between the couple line to change the performance. So as you can see, I already did the tuning, because if I try to do it in the video, it will take a lot of time, and we have a time limit by 10 minutes. So I will try to explain you fast about this. So as you can see, this is a bit different than what the previous results has been shown. This is done because of the tuning. I needed to shift this S21 result a little bit, so it can cover our F low and F high. So as you can see, it's pretty close to our F low and F high that you see at the beginning of this video, and you can see our the attenuation and the gain of this filter, and also the tuning is pretty easy to do. You just need to press on this icon. It will show you this window, and then you can choose the parameters you want to use, and then you just play around. I will show you some demo about that. And if you can see here, if I play around with this, it will change the values. But even though I already did that, what you need to do is you just need to play around until you get the result that you want. And if you mess up, it's okay. Like you see, if I can play with this one, it will mess it up. You just press restore values, and it will revert all the change that we've done. And as you can see, I changed most of the values for this project. And I give you a simple advice is to work on the W and the S more than the L, because if you can see the L have a really big difference and it will mess up the results that you will get. So be careful when you deal with it. Don't change a lot, because as you can see, if I change any of the L, it will mess up the frequency so hard and we will not get what we wanted. So try to play with the S and the W, because the effect is minor, especially if your design in the first place you calculate it correctly. So we'll get a pretty much close result. So I guess we just left on one step. I will let you hear from my friend about it.
Okay, thanks to my friend for the explanation. And now we want to do a generating for the EM. So we want how to generate the layout or the EM. We go to layout, generate, update layout. This option, then click and also OK. So here we get we generate. This is the layout, as you can see, the P1. So here's, as you can see, the difference between CLN1 and CLN2, the space between them, is because we played with the toning. So we play with the toning to get the response, actually the response we want. So that's the reason why we can see the differences between each one, because of the toning that we played to get the response we want.
Okay, guys, now we reached the end of our explanation for this video design. You can have a look on our circuit on our cable line. You can of course reference this to design a similar band bus filters. You just need to play around with the calculation. So I will show you now.
Yep, this calculation, we start with the filter order, which is three, not five, by the way.
Sorry for this
Sorry,
mistake.
this mistake. So, and the filter response, which is equally ripple, 0.5 dB, and maximum return loss minus 15. And also, we don't forget that the frequency, the center frequency, which was 881.5 megahertz.
You can easily calculate the center frequency using this formula. Just put your upper and lower frequency
Yep.
and divide by 2. Also, the fractional bandwidth is really important for this calculation to help you get into impedance interval. And then
This is the impedance odd and even.
that will
You can
help us
see
to
Yep.
do the calculation in the line calc from here. This is just a quick recap for what we do, and you can go to the beginning of the video to see how to use this one. And this is our result, guys. As you see, uh, this is a pretty good performance for this filter. Even though we use just we just used a three order filter, but the response was
The one
pretty much good. And I guess we fulfilled our goal of designing this filter. So thank you very much for watching.
Thank you, guys.